Hi there and welcome back to the College Physics series. In today's lesson, we're going to be talking about coordinate systems and how they allow us to dive deeper into vectors. So on top of that, we're going to learn how to calculate what we call vector components and how we can use them to simplify complex sounding questions. Before we get started, be sure to download the guided notes that are in the description. Use them to follow along with me in today's lesson. Thank you for being here. And let's get started. In our last video, we learned how to add and subtract vectors graphically. But as we begin this lesson, it's important to note that while working with vectors graphically is helpful for visualization, it's not always the best way to find accurate quantitative results. Today, we'll dive deeper and explore a coordinate description of vectors. This will be the foundation for performing vector calculations more effectively. Let's start by discussing coordinate systems and how they help us organize and calculate vectors. The world doesn't come with a coordinate system attached to it. A coordinate system is something we artificially impose on a problem to make quantitative measurements easier. The right choice of a coordinate system can simplify a problem significantly. One of the most common systems we'll use is the Cartesian coordinate system, which is the familiar rectangular grid with perpendicular x and y axes. In this system, the x-axis represents horizontal movement and the y-axis represents vertical movement. Together, they allow us to describe the position and motion of an object. One thing to note is that in the Cartesian coordinate system, the x and y axes meet at a point called the origin. The origin is a point that we represent as 0, 0. If a car moves 4 meters horizontally and 3 meters vertically, where would it be located on this grid? Using the grid that we already have, I can mark the x-axis by meters and the y-axis as well. So in this example, the car moves 4 meters horizontally. So I end up 1, 2, 3, 4 units away. And then it moves 3 vertical. So that point would represent 4 meters, 3 meters. The 4 represents the x value, and then the 3 represents the y value, because when we write a coordinate, it's always x, y. So this coordinate would describe the position of the object at the end of its motion. Let's see how we use this coordinate system to break vectors down into their components. Any vector can be broken down into 2 smaller vectors called its components. One component lies along the x-axis and the other along the y-axis. These 2 components together represent the original vector. Let's imagine a car moving up a hill at an angle. Instead of working with a single vector, we can split the movement into 2 components. One component shows the movement along the x-axis, and the other will show the movement along the y-axis. So where this car first starts, let's label it this point. It touches the x-axis around there, and I'm going to call that my initial horizontal position. At the very end, it's going to touch along there on the x-axis. That'll be my final position. I can draw the displacement vector for this horizontal motion. It's just an arrow that points towards the right. And this arrow would represent the horizontal displacement of the car. I can do the same thing for the vertical motion. This point meets up at about here, where it initially begins vertically. And I can do the same thing for the final position. So starting from the initial, I can draw the vertical displacement vector to the end. Together, they both represent the actual displacement for this car. So if you imagine me sliding up this vector right here, this vector can be slid up to right here. This vector represents the horizontal displacement, and I can slide this vertical one over here as well, where it belongs. And all together, they form a right triangle. Let's visualize how we can break down any vector into its components. Let's say I have this vector that we're going to call A. I can represent the components of this vector by beginning at its tail and drawing down until I meet the lowest point of the vector. So that would be the lowest point here. And I can draw the horizontal magnitude of this vector by drawing this towards the right. This would represent AX, and this would represent AY. That is how we write out the horizontal and vertical components. We can also do this for vectors that point in any direction, such as this one. I will call this vector B. And I can determine the vector components just by drawing a line straight up. This would represent the vertical component of this vector and a line pointing towards the left. Not a line, but an arrow. This would represent the horizontal component vector. All vectors will always have an x component and a y component. But what about vectors that are horizontal, like this? I call this vector c. Well, it has an x component, and that x component is equal. These two are equal. But the y component is non-existent. It is the zero vector from the previous lesson. It doesn't exist. And the opposite is true for vectors that point straight up or down. Vectors that point straight up or down will have, I'll call this vector d, will have an x component equal to 0, but the y component will be equal just to the entire vector itself. In general, the rule of thumb is that if you want to find the resultant of any vector, you're going to find the sum of the vector components. That is the main rule. Now that we understand the concept of vector components, let's explore how to calculate them. If we know the angle and the magnitude of a vector, we can find its x and y components using basic trigonometry. The one thing that you're going to have to remember is the mnemonic SOHCAHTOA. If you're unfamiliar, this mnemonic just helps you to memorize the equations for sine, cosine, and tangent. The way that you utilize this mnemonic is that it's split up into threes. The SOH is supposed to help you remember that the sine of an angle is opposite over hypotenuse for any right triangle. The CAH, the CA, is supposed to help you remember the equation that the cosine of an angle is equal to the adjacent over the hypotenuse. And then the TOA is supposed to help you remember the equation that the tangent of theta, or the angle, is equal to the opposite over the adjacent. Now, for us, we do not have a definitive set of equations. We can see them in two different ways, though. And I'm going to go over two ways in which you can see these components and these formulas. The first version is when your angle is directly to the left or to the right. So it could also be something like this. Directly to the left or to the right of your 90-degree angle. Let's separate them like this. So you can see it either one of these ways. But remember that the legs of a right triangle we call A and B, and the hypotenuse is always C. But for us, we are using vectors. So I'm going to call these vectors AX, AY, and then A, where A without the vector symbol on top is just the magnitude of that vector. And I'll do the same to the other side. So if your angle is to the right of the 90 degrees, you need to identify your opposite and adjacent. You can easily identify your opposite and adjacent just by starting at the vertex or the corner in which your angle is at. All you have to do is draw a line starting from the vertex directly across. That value will be your opposite. Of course, your longest side is always your hypotenuse, which leaves the last side to be the adjacent. Remember, at the beginning I said, let's see how we can calculate these components if we know the angle and the magnitude of the vector, which is the hypotenuse. What this means is that for me to find my AX, I'm looking for the adjacent side, I know my hypotenuse, and I know what my angle is. So this means I have to use the cosine, and I'm going to follow this formula. Now that I have this formula, I'm going to plug in my adjacent and my hypotenuse. Now to solve for my x component, I'm going to multiply by a on both sides of the equal sign. It's going to cause these to cancel. Therefore, to calculate my x component in this setup, it's just going to be the magnitude of the vector multiplied by the cosine of the angle. So when you have a right triangle in this orientation here, where the angle is to the left or towards the right of the 90-degree angle, then this is the formula that you're going to follow in order to find that x component. Now, how do we find the y component? Well, that means we're looking for the opposite. And we know the angle. So therefore, if I'm going to find the opposite, I'm going to use the sine. Now I'm going to plug in my opposite and my hypotenuse. And again, to solve for ay, I'm going to multiply by a on both sides of the equal sign. Therefore, my equation for the y component is just going to be the magnitude of the vector a multiplied by the sine of theta. And that is how you calculate the x and y components given the magnitude of a vector and its angle. The horizontal component uses the cosine, and the y component, the vertical, uses the sine. However, in physics, you're not always going to see triangles in this manner. So let me go over the other way. Let's say I have vector A that points in this direction. I can find its components graphically just by drawing a line down. So this is going to represent AY and this is going to represent AX. But this time I'm going to call my angle alpha and it's going to be on the top corner. But this time the angle is directly up from the 90-degree angle instead of left or right as the way we saw in these first two cases. All I have to do is flip this triangle upside down to get the opposite version. In this case, I need to identify what my opposite and what my adjacent are. So from the angle, this is the vertex, the corner it's backed up into. So from there, I draw a line directly across and that gives me AX to be my opposite. I know my A, my longest side, is always my hypotenuse. Therefore, my AY is my adjacent side. Using SOHCAHTOA, I can follow the same procedures as before. Given the magnitude of the vector A, the hypotenuse, I know all the H's, and I know what the angle is, so I have the inputs at the beginning of each function. But if I'm looking for my AX, that's going to be my opposite. So now to find my AX, I'm going to use the sine. So the sine of the angle is equal to opposite over hypotenuse. Plugging in my symbols that I have for this triangle. So the sine of the angle is equal to opposite, that is AX now, over the hypotenuse, which is just A, the magnitude of the vector. To solve for AX, I have to multiply by A, and I'm going to get that my horizontal component is now A times sine theta. As you can imagine, you can follow the same process for AY, and you're going to get A times the cosine of theta. Notice how everything is very similar, but only one thing has changed. The placement of the angle is the only thing that's different. When the placement of the angle is along the vertical, as it is in this triangle down here, you're going to use these versions of the equations to solve for the x's and the y components. But if your angle is next to the horizontal, then you're going to use these two up here. I hope that's clear. I definitely do not want to say use this formula whenever to find the x component, because it depends on the scenario that you're given. So there is no formula to memorize for x components. It depends on the triangle that you have and the placement of the angle. It's totally dependent. But I hope this clarifies why we use each version. One quick note that I need to make is that the y component is pointing downwards. Therefore, this must be negative. So here I'm going to get negative A cosine theta. So if I have a triangle that has a leftward component for the x, that is going to be negative. But in this case, it was pointing towards the right. Therefore, it remains positive. So if it's pointing left or down, those cases will be negative. Negative values for AX or for AY. So please keep that in mind. Let's work through an example. Imagine we have a vector with a magnitude of 15 meters and an angle of 35 degrees from the horizontal. Let's calculate its x and y components. To do that, I can place a Cartesian coordinate system. My vector is going to begin at the origin, and it's going to have a magnitude of 15 meters at an angle of 35 degrees from that horizontal. Now, given that the magnitude of this vector is 15 meters, I'm going to call it vector D because this represents some displacement. And I can break down this vector into its x and y components. I know it's going to have a horizontal piece, which I'll call dx, and a vertical piece that I will call dy, with this angle being 35 degrees. In order to calculate these vector components, I need to determine whether this angle measure is towards the left or right, or up or down from the right angle. In this case, it's left. So back over here, if I have an angle measure that is left or right, I'm going to be using these two formulas. The x gets the cosine, the y gets the sine. And these are the formulas I'm going to use to calculate its components. So in this case, dx is going to be d cosine theta, and dy will be d sine theta. Now plugging in the numbers, the magnitude d is just 15 meters times the cosine of 35 degrees. One quick thing I need to note is that your calculator must be in degree mode, not in radian mode. If your calculator is in radians, you're going to get an incorrect answer for this angle. Plugging it into the calculator, our dx should be 12.3 meters. And our dy should be 8.6 meters. These x and y components tell us how much of the vector is in the x direction and how much of it is in the y direction. Let's do another example. This next example reads, a hiker is navigating through a dense forest. She starts at point A and moves 4 kilometers east to point B. From point B, she then moves 3 kilometers north to point C. Represent the hiker's movement from point A to point C as a vector. Calculate the angle that this vector makes with the east direction. So I could represent this motion using the Cartesian coordinate system. It's just simple left, right, and up, down. So the hiker goes 1, 2, 3, 4 to the left to point B. Point A, we're always going to call the origin. It's always best to call the starting position the origin. And then the hiker moves 3 kilometers north to point C. So to represent the movement, the overall movement as a vector, I'm going to draw an arrow beginning from the origin to the final position. This would be indicative of this hiker's displacement. Just a straight line from the initial position to the final position. Now it wants me to calculate the angle that this vector makes. This can sound tricky and it might look a little bit tricky, but it follows the same SOHCAHTOA rules. Here's what I know. I know that the x component has a magnitude of 4. And I know that the vertical component is 3. And I want to find that angle. If you want to find angle measures, you could also use SOHCAHTOA. Let's define what's opposite and what's adjacent and what's hypotenuse. So hypotenuse is always the longest side. I do not know what that is. Therefore, I know my opposite and I know my adjacent. Remember, opposite is just a straight line directly across from the vertex in which the angle is cornered in. So I know my O's and I know my A's. And I'm looking for the angle measure. Therefore, I'm going to use TOA. And that stands for the tangent of an angle measure is equal to opposite over the adjacent. Well, how do I solve for the angle measure? Because remember, the tangent is a function. Theta is an input to the tangent function. Let's do some quick replacement and I'll explain exactly how we do this. So the tangent of theta is equal to the opposite, which is 3 over 4. It's a few steps, but let me go through them one by one. Step number 1, you're going to take what's on this side of the equation and you are going to replace it inside the parentheses there. At the same time, you're going to take what's inside this parentheses in the tangent and you're going to replace it where the other value is at. You're going to swap those two values. So the 3/4 is now going to belong inside the parentheses of the tangent. It's going to become the input to the tangent function. And the angle measure is going to go to the right-hand side of the equation. That's step 1. The second step is that we're going to add an inverse symbol on the tangent. And that's it. Altogether, this is what it looks like. Tangent to the -1, and this -1 is not an exponent. It just represents that this is the inverse function of tangent. You can call it arctan or you can call it inverse tangent. Now the new input is 3/4, and this will be equal to theta. And that is how you solve for the angle measure, only having to remember SOHCAHTOA. And you can repeat this process with the cosine and the sine to get the inverse sine and the inverse cosine. The relationships and the process are all the same. So in your calculator, you're going to have to find the inverse tangent button. And your input to that function is just going to be 3 over 4. Our angle measure should come out to be 36.9 degrees. And that is how you find angle measures using vector components. Once we have the x and y components, we can recombine them to find the original vector again using the Pythagorean theorem. And that looks like this. So this is that old formula from Algebra 1 that we learned probably a while back, but it's very important to us here in physics. Remember, when we're dealing with a right triangle, the A and B represent the legs, and it doesn't matter which one you call A or which one you call B. The thing that matters is that your hypotenuse is always C. For example, if we know that the x component is 12.3 meters and the y component is 8.6 meters, we can find the magnitude of the original vector by using the Pythagorean theorem. So this vector, we'll call it D, and this is going to represent the hypotenuse here. So in the formula a squared plus b squared equals c squared, I'm going to replace my a and b. So a will be 12.3 meters squared plus b, which is 8.6 meters squared. And I'm calling the hypotenuse letter d, so I'll call it d squared. Because meters, a measurement in meters, is indicative of a distance or displacement. So I'll use the d to represent that. 12.3 squared is going to give me 151.6 73.29 square meters plus 8.6 squared is going to give me 73.96 square meters. All of that's equal to d squared. The sum here on the left-hand side is going to be 225.25 square meters. That's equal to d squared. Finally, to solve for d, the magnitude of my hypotenuse, or that displacement vector, I'm going to get d equals to 15 meters. And that is how I can get the magnitude of the original vector only using the vector components. Let's quickly talk about the algebraic addition of vectors. So far in our lessons, when we've been dealing with vectors, we've been dealing with pretty simplistic vectors, ones that go only left or right or up and down, and the scenarios are pretty basic. But what happens when things get complicated? Let me tell you a better method to add vectors, and you can use this method to add any number of vectors that you want. It could be 5, it could be 100 or more. The general rule to find the resultant vector is that you're going to find the vector sum of all the vectors that you're adding up. If I add vector A plus B plus C plus any other vectors in my situation, the resultant is going to be just a line from beginning to end. And that's what I'm going to call R. Here's the neat thing about vector components. The neat thing is that we can build this resultant using the components, because the resultant R is going to have components Rx and Ry. Remember how we mentioned that every vector has an x and y component. So the x component of the resultant is just going to be the sum of ax plus bx plus cx and so on. For each vector that you're adding, you're just going to add all the x components together. Once you add up all the x components for each individual vector, the sum will represent the x component for the resultant vector. The same idea applies for the y direction. I'm going to add up all the y components for each and every vector that I'm adding up, and the answer is going to be the resultant vector's y component. Let me show you a picture to help clarify this. Let's say this is my x direction, this is my y direction. Let's say I'm adding two vectors that are in not so nice directions. Starting from the origin, I have vector A that points in this direction. Then on top of that, I'm going to add vector B, which maybe it's going to start from here and it's going to head in this direction. Remember, my resultant vector starts from the very beginning and it points in the direction of the very end. I'm going to call this resultant vector C. Well, how do I use the Pythagorean theorem here? How do I calculate the x and y components? This becomes a lot more difficult, but in reality, it's a lot easier if I use vector components. The idea that I'm trying to explain here is that all that you need to find are the x and y components for each individual vector. So this horizontal piece will be ax. This vertical piece will represent the vertical movement of the first vector A. The same thing applies to vector B. From vector B's starting point, which is here, because it comes down from this point, that's its initial horizontal position. It then extends all the way up until this point. It comes down from here. And this would represent the x component for vector B. And I can do the same thing for the y. So vertically, vector B starts here, and vertically, vector B ends right here. And this would be by. So the idea is that from the beginning of vector A all the way to the end of vector B, that will be the x component of vector C. Because if I notice, this is how far horizontally vector C has traveled. And this will be how far vertically vector C travels. So from here, this gives me cy, and that is just ay plus by. And here gives me cx. To find that, I just need to add ax and bx, plus any other x component for any other vector that I want to add in there. So let's separate this image. So essentially, I found the magnitude of the components of vector C by just adding the individual x components for each vector. And I found the y component cy by adding the individual components of each vector that I was adding up in there. In this case, A and B only. So this is going to be the general rule for adding vectors algebraically. So using this method, I can add 5 different vectors, and I just need to find the x and y components of each one. And when I add them all together, I'm going to get the component for the resultant vector. X is for the horizontal, y is for the vertical. In some problems, like when dealing with ramps or slopes, it's useful to tilt the coordinate axes to make the calculations easier. Instead of using the usual horizontal and vertical axes, we rotate the axes to align with the incline. For example, imagine a box sliding down a ramp at a 25-degree angle. So here we have a box sliding down, and this ramp is at an angle of 25 degrees. Our typical X and Y axes will point straight up and straight to the right. What we're going to do is that we are going to tilt the axes so that the x-axis runs along the ramp and the y-axis is perpendicular to it. And by doing that, we're going to simplify our calculations. Let me show you how we do that. So there we have the original box going down the slide. Here's going to be my origin. My x-axis is going to run completely parallel to the ramp, and my y-axis is going to point perpendicular to the ramp. Now, one component of the motion is parallel to the ramp, which would be the x direction, and the other is perpendicular, which is the y. This approach makes solving problems involving inclines much simpler, and you'll be working with motion in the direction of the ramp rather than across two different sets of axes. And we'll see more examples of this in the next video. Now let's apply what we've learned with a few practice problems. The first example reads, a cyclist moves with a velocity of 18 meters per second at a 60-degree angle above the horizontal. Calculate the x and y components of the cyclist's velocity. Well, I can easily picture this using a Cartesian coordinate system. Beginning at the origin, I have a magnitude of 18 meters per second at a 60-degree angle. Now I can draw this separately on the side. So the magnitude would be v equals 18 meters per second. Here's my angle measure. And I can fill in the x and y components. Here will be the x component, vx, and here will be the y component, vy. Notice that my angle is to the left of the right angle. So therefore, my vy is going to be v sine theta, and my vx will be v cosine theta. All I have to do is plug in these values into the equation and let the calculator speak for itself. So v is 18 meters per second, and it's going to be times the sine of 60. For the horizontal component, it's going to be 18 meters per second multiplied by the cosine of 60. My vy is going to end up being 15.6 meters per second, and my x component is going to end up being 9 meters per second. And this makes sense because my vector is more vertical than it is horizontal. So it makes sense that my y component is greater than my x component. Let's do another example. So the second example reads, a drone takes off from a charging station and flies 150 meters due north to a waypoint. From there, it flies 250 meters southwest to another waypoint. Represent the drone's movement from the charging station to the final waypoint as a vector. Calculate the angle that this vector makes with the north direction. So now we have a problem that isn't so easy looking. I can visualize this motion first using a Cartesian coordinate system. So upwards is going to be north, down is south, to the right is east, and towards the left is my west. So I know initially the drone, I'm going to label its starting point as the origin, and it's going to go 150 meters due north. Then it's going to start from here and head 250 meters in the southwest direction. I don't know how far it's going to end up because all I'm doing is representing this graphically, and I don't have access to many quantitative values yet. But this is all that I know. So it wants me to represent this final resultant as a vector. So the resultant's going to start from the very beginning and point in the direction of the very end. So I'm going to call this resultant vector C. Well, how do I find out what this resultant vector C is? And I need to calculate the angle it makes with the north direction. So all that simply means is that I'm going to treat my north direction as a starting point, and I need to see what angle measure that makes. And that's simply it. So in order to find vector C, I need to add up the x component and the y component. Well, here, my vector C is made up of two different vectors. So therefore, I know that my Cx is going to be equal to Ax plus Bx. Let's label this vector A and vector B. And my Cy is going to be equal to Ay plus By. So let's analyze each individual vector. So vector A is just 150 meters towards the north. So my Ax is going to be 0 because I have no horizontal movement. But my Ay is just going to be positive 150 meters. So I know what those are already. Next, I need to figure out what vector B is. I know that the magnitude is 250 meters. And notice that it says southwest. When it says southwest, it is exactly in between south and west, and therefore it creates a 45-degree angle with either side. So that's something that I know. So when I'm recreating this right triangle, let me just create it like this for the picture's sake. I know that up here is a 45-degree angle. Notice that this 45 degrees is upwards of my right angle. Therefore, if I'm going to find my by and my bx, I need to go back and I need to remember that it is flipped for this type of situation. It's in this situation here where I need to use these formulas. I'm going to copy them and give them to us here. Therefore, my bx is going to be b sine theta. But because it points towards the left, it's going to be negative. by is going to be b cosine theta. But because it points towards the left, it is also going to be negative. Therefore, I'm going to get negative 250 is the magnitude of b times the sine of 45. And then by is going to be negative 250 meters times the cosine of 45. What you're going to get is the exact same answer for both of them, negative 176.8 meters. And the reason why that is because a 45-degree angle is exactly halfway, so it shares the x and y components equally. Now that I have ax, ay, bx, and by, I can plug them in to the x and y components of the resultant vector. Therefore, my cx is just equal to bx, which is negative 176.8 meters. And my ay is 150 meters, and I'm adding negative 176.8 meters. Therefore, cx is equal to negative 176.8 meters, and cy is going to be equal to negative 26.8 meters. Now, using this information here, I can construct vector c. Well, we see it here already. Let me zoom it in so that we can take a closer look at it. So this is vector c that I'm interested in. What I just learned is that cx, my horizontal component, was negative 176.8 meters. And my vertical piece that points downwards, my cy is equal to negative 26.8 meters. What I'm finding is the angle from the vertical all the way to here. That's pretty simple. I already know that between north and west, this creates a 90-degree angle. So all I have to do is figure out what this angle measure here in the corner is, and I'll call it theta. So it's going to be 90 plus whatever theta is. So luckily, I know that from this angle measure theta here, I know that this, from this corner, is my opposite side. This is opposite. This is always my hypotenuse, the longest side. Therefore, this cx is my adjacent. Therefore, I know opposite and adjacent, which means I'm going to use the inverse tangent for this one. So my angle measure is going to be equal to the inverse tangent. And here's the thing when calculating angle measures with negative components. We're going to use the absolute value to keep it positive. My opposite is cy. My adjacent is cx. Therefore, I'm going to get the inverse tangent. Cy is 26.8 divided by cx, which is 176.8. The calculator will give you an answer of 8.6 degrees. That makes sense because this is a tiny, tiny angle right here. So this is 9.6 degrees in this tiny corner. Remember, the question is calculate the angle that this makes with the north direction. Starting from the north, I travel 90 degrees plus an additional 8.6. So in total, this angle is 90 degrees plus 8.6 degrees. That's going to be 98.6 degrees. And that will be the answer to this question. The overall idea here in question number 2 is that we had to use vector components to construct our resultant vector. And then we had to use trigonometry the way that we did in the previous examples earlier to calculate the angle measures and the x and y components. So essentially, we put everything that we learned today all together in this practice problem number 2. Here is a problem for you to try on your own. The try it yourself problem reads, a hiker walks 120 meters southwest, then 60 meters east. What is the hiker's net displacement? Remember, displacement is a vector quantity, so your answer is going to look like this form. So you're going to get a magnitude with a direction, and that will be the final answer for that. That wraps up our lesson on coordinate systems and vector components. Today we learned how to break down vectors into their x and y components using coordinate systems, and we explored how tilting axes can make certain problems easier to solve. If you found this lesson helpful, please consider liking the video, subscribing to the channel, and sharing it with others who might benefit from it. Also, don't forget to leave your answers to the Try It Yourself problem in the comments. I'd love to see how you did. Thank you for watching and being a part of the College Physics series. I look forward to seeing you in the next lesson.